Okay, my today's presentation is about hearing aid. Using the SEAforth, and of course it's not that cool as the music synthesizer I presented the last year, but it's still very interesting, and it was, really, fun, to develop it because we had a lot of challenges. Yes. Yes. Well, actually, the microphone is for the video recording, but I'll try to be louder. Yes. Thank you. The point was that hearing aid is not that cool as the music synthesizers, but it's still a very interesting application, and it was, we had, real fun implementing it because there was a lot of challenges, engineering challenges, mathematical challenges, and it's still a very interesting project. And of course, we use the SEAforth, and we really, proved that SEAforth is able to create the really great applications, and SEAforth much better than all the other existing processors in this field. So I'll show you. And okay. So well, actually, I'm not real expert in this field in hearing loss, and I read a lot last week about this thing to explain to you. And I figure out that if you don't understand the things very well, then you're a pretty good lecturer, because you don't dig very deep, and your students, understand your simple language, because all you can say is simple language, and simple language is, you just cannot, speak complicated categories, so people understand you. So I think I will explain the thing about the hearing loss very well, but then when we got, into the programming details, I could, dig a little bit deeper than you want me to do. So please, ask me, to slow down and, explain a little bit more than I did. Anyway, our ear basically consists from 3 parts, and it's very simplistic. The outer ear, and the middle ear and inner ear. And basically what's going on, the outer ear and middle ear connect the inner ear to the outer world. So basically this is the mechanical connection which connect the sound pressure into the cochlea. And cochlea is very important part, because cochlea basically is the converter which converts the sound pressure into the electric signals. And these electric signals with the auditory nerve goes to the brain. So this is how we hear. You've got the mechanical channel, you've got a converter from mechanical signals to the electric form, and you've got the electric channel, or the nerve channel. And depending of which part of the system is damaged, we deal with a different kind of hearing loss. So if something broken with your outer ear or with your eardrum, then we deal with conductive hearing loss. If cochlea is damaged, then you've got sensory hearing loss. And if your nerve is damaged, then we deal with the neural hearing loss. And in today's presentation, we deal with the sensory hearing loss when your cochlea, or analog to digital converter, is damaged. So we go and look closer to the cochlea. Sorry. So basically, cochlea is a snail-like or spiral-like device which execute 3 different functions. First of all, it's a bandpass filter. It takes the sound pressure by passing, toward, this spiral-like trajectory, and then it activates different nerves according to the different frequencies. The other function Cochlea does is detection. And basically detection is understanding how loud each frequency are. It's very similar to the radio detection when we are using the diode trying to understand the envelope of the signal. So basically detection is the figuring out the envelope of the signal or the magnitude of the signal, how loud it is. And the third part is the compressing. So using the detected envelope, we're trying to amplify the weaker sound to make the dynamic range of the sound smaller. The thing is that biologically or physically we cannot hear more than 60 or 90 dB range, and still, in a book says that the dynamic range of the sound people can hear or can recognize is 140 dBs. How it happens? Because inside the cochlea we compress this dynamic range, so it goes to your brain in compressed form. So basically we have a band pass filter, we've got a detection or magnitude analyzer, and we've got a compressor. And when this cochlea is damaged, one of these functions doesn't work very well. So it just goes down completely or partially. So to compensate this kind of damage, you have to recreate this functionality with some electronic or artificial device. And well, this is common knowledge that to compensate this kind of hearing loss, you have to design something like this. So you have to design the mechanical or analog or digital device which basically have a multiple frequency bands, multiple automatic gain control devices which are compressors, and multiple amplifiers which control separately the gain for every band. Well, but what people do differently is, how exactly you implement these components. How many bands you're going to implement, what the algorithm and what the parameters of the automatic gain control you use, things like this. And I'm not going to discuss or question the particular algorithm we used, because my focus today is how we implement this algorithm, how we port it into the our particular chip. And just because I'm not the author of this algorithm, we worked together with our Austrian Vienna team, and the algorithm was developed by Dr. Zlatan Ribic, who in the field for 30 or something years. So we just were given with this algorithm, and we thought, what, this is the best in the world algorithm. He's supposed to help people with the hearing loss better than any other algorithm, and your task is just to implement it the way it is. So they provided us with the MATLAB model and all the they implemented the prototype in a C using the Texas Instruments DSP board, and later I'll show you the size and the power consumption of this device, because it's going to be pretty nice comparison to the SEAforth. But the point is, I'm not going to discuss this algorithm. I just will describe to you what the task we dealt with and how we implemented it. So first part of the algorithm is the band. So first of all, we needed to implement 8 band filters with this the parameters. This is the hertz. And very important part of the description of this filter were the slopes, left and right slope of the filters. So transition band supposed to be sharper than to the left, supposed to be sharper than transition band to the right. So, and the way it's supposed to be, the point of the start of the pass band of the next band supposed to match the point of the start of the transition band when it dropped 60 dB of the gain. Well, so this 60 dBs at this point, and 30 dBs at this point, is a very important part of the algorithm, because according to the hearing loss model, this is the way how you compensate how you introduce the frequency masking, and frequency masking is very important part of the how to recreate the understandable speech. Yes.
On your band filter, your bandwidth to center frequency, is it a constant throughout the filter bank? The Q?
Well, actually, no. This is a logarithmic scale. So, which part are you talking about? Yes, in a logarithmic scale, it's constant. In a logarithmic scale, so it's I think it's 1/3. Yeah, it's constant in a logarithmic scale. So, and this is the signal diagram of the filters. And basically, it describes, how the band 1 is implemented. So we used the standard second order sections to implement the filters. So who dealt with the digital signal processing, he knows about the things. And the challenge was to pack as many second order section as possible to the single core. And we figure out how to pack up to 5 second order section into this two cores. And it wasn't very easy, because we're talking about the resolution we're talking about is 36 or 35 bits. And it's not very easy to implement, even to fit even one second order section into the single core, but we figure out how to fit 5 of them into the couple cores. And the thing is, it's pretty general purpose filtering. So right now we're using it for the hearing loss hearing aid device, but in theory it could be used in all kind of devices related, where filters are, needed. So it's just general purpose brick you can use to build different kind of filters. And so this is the signal diagram of the band 1, and this is the first part of the bands, from 2 to 7. So you can see that we will get 3 sections for the high pass filter, and we'll get 2 sections for the low pass filter. So altogether we'll get 4th order filter for the high pass, and 6th order filter for low pass, and 6th order filter for high pass. So it's pretty good filtering. So, and this is how the band 8 looks like. So basically we've got a macro, and we just populate this macro into the 16 cores. And I'll show you the floor plan later. So you will see how this kind of processing mapping to the SEAforth. The other important part of the algorithm is a compressor. And this is the the way we're doing this compressor. The very important part of this compressing scheme, it's instant. You don't need to accumulate the period or more than one period of the signal to figure out its envelope. We can figure out the magnitude of the signal, with one sample delay. And I'll show, and this is because we've got this analytic signal calculator, which basically convert the input signal into the complex form. So we've got the imaginary and we've got the real part. And of course, if you calculate the hypotenuse of this imaginary and real part, the magnitude of the vector, you'll get your envelope instantly. And yeah, it says that you should take a square root from the sum of the squares, but we do it differently. And if I'll have time, well, actually, yeah, I can tell it right now. So we don't use the square root because it's an unexpectedly complicated routine. So we decided to use a different algorithm. So we're using the Corsic. And this is a very interesting story because, when I just started working with the machine force, a long time ago, yeah, I started with the Corsic, to calculate the sine. And by then, we got very impressive results. It was much faster than the 387. And 387 was the coprocessor. So we could calculate the sine much faster than 387. And then I got frustrated a little bit about the Corsic because it was slower than the algorithm based on the lookup tables. But then, recently I figured out that it's still good for example, for this kind of calculation because we didn't have enough space to allocate to place the lookup table to calculate the sines and cosines. And we had a pretty higher precision requirement. So we had to calculate the magnitude with at least 18 bits of the accuracy. So Corsic, worked for me, pretty good in this case. So instead of this thing, we have Corsic calculating the magnitude. And well, this is just normal the add operation, and this is the exponential. And of course, we calculate the exponential using the logarithm and exponent function. And it was pretty easy too because I probably mentioned before that inside our ROM bias we have a polynomial function which help us with the complicated math. So implementing the logarithm and exponential was pretty straightforward. And of course, yeah, I had the hard book with all this tables, and Chuck mentioned that this is the book everyone is supposed to read, so we did. And then we have this part. And it's very important that we use division. Because initially we said, okay, who is interested in the division? Because if you divide by, well, if you can reverse the number you're going to divide by, then you can use the multiplication. And when you're talking about the fixed point, it's not true, it's not equivalent, because you lose your accuracy on the edges of your dynamic range. So sometimes division is better than multiplication. It's, in theory, yes, divide is just to multiply by reversed value, but in the situation when you deal with the fixed point or integer arithmetic, the division is still better. Sometimes it's better than the multiplication. And fortunately, we've got the division in our ROM bias too. So a lot of things which looks relatively complex was not that complex for us because we got very good ROM bias. And this is how Yeah, I promise you to explain how this component working, an analytic signal calculator. This is explanation how it's working. So basically we have all-pass filter. And the thing about all-pass filter, it doesn't filter the frequency. It just changes the phase characteristic of the signal. So if you have two all-pass filters with slightly shifted phase, and if the difference of the phase for every frequency, for the working range are p divided by 2, then you can consider it as the not complicator. I don't as the converter from the real signal to the complex form of the signal. So yes. Yeah, could be. Yes, absolutely, yes. So well, this is Well, when I was trying to understand how old this idea is, so it went back to 70s. So people were playing about this idea even before the digital revolution. So this goes back to the analog circuitry. But this is a very nice idea, and this is how we do the instant compression. Because to do the compression, you have to figure out the magnitude of the signal. This is the way how we do it with only one sample delay. So this is a very nice idea. So I dedicated the whole slide to this idea. And another one part of the how many time okay. So another one important part of the device, hearing aid device, is the directional microphone. This is not the part of the which compensate the damaged cochlea, but directional microphone is very important part because it's helping the people with the hearing loss to point to focus on the sound they are interested to listen. So yes, it's not a part of the cochlea damage compensation, but it's very important part of the device, and this is how we do the directional microphone. So basically what's going on is we have these two components which are subsample delay. So it's not like z minus 1 in the previous picture, because we're talking about the 20 microseconds delay. And in our case, when we have 32 kilosamples per second sample rate, we're talking about the delay shorter than the distance between the sequential samples. And the way we're doing this delay is we using linear Lagrange interpolation. So how it's working? So basically, what happens is you've got the two signals from the two microphones, rear microphone and front microphone. And the distance between these two microphones is in our case, 7 millimeters. And 7 millimeters is about 20.5 microseconds delay. So if you have the signal coming from the front, then you've got the difference in the phase between the rear and front and rear, 20.5 microseconds. So if you shift it, and if you delay it and you reverse it, then you've got the signals subtracted from each other. But you still got some difference, so it's not subtracted to the zero. But if your signal is coming from the rear, then your shift, your delay, compensate the actual delay of how signal is coming to the microphone. So you basically subtract one signal from the other signal, with the same phase. So you've got zero. So you've got kind of a cardioid of the directional. So this is very simplistic explanation, but this is how we do it. So And this is nothing special new. So people do this sub-sample delays to build a directional microphone for a long time. Yeah.
Do you do this inside a chip?
Yes.
Outside? Inside a chip?
Yes, we do it on chip. So we've got so everything is done on chip. Okay, and this is how we map it to the SEAforth. This is a very interesting slide because I didn't draw it myself. So what we did is we just ran the simulation in VentureForce simulator, and we just read the statistic, how many clocks each core is active, and we collected the statistic, how the cores communicate between each other, and based on this collected statistic, how busy each core was and how they communicated to each other, we automatically build this heat map. So we built it automatically. And this is SVG we generated. So it's a little bit different from what Dennis told us, but SVG is a very nice protocol language to generate. So when the first version using HTML, but then we decided that HTML is not a good thing because it's even SVG is not very portable. It's different, when it's displayed on Firefox and the Safari and the Chrome, but still it's much better than HTML. So we decided to go with SVG. So this is the heat map of the real Hearing 8 application running in a simulation mode. So you can see that most of the cores are pretty cold. You see, this is the red is the 100% busy core. The black is not core which is not used or almost not used, and the magenta or green, it's something, it's 50% busy. So if you calculate the business of the cores in general, it will, be about 19% busy. So the good thing about SEAforth is it's very powerful chip. It can provide you with up to 28,000 MIPS. Okay, but what if I don't need 28,000 MIPS? What if I need only 3,000 MIPS, like in this case? Okay, I don't run it that hot, but I will not consume the power. So every ops counts. And recently I was talking to some guys who are really involved into the server farms, data centers. And they told me that the biggest problem with this server farms or this data centers, because the standard Pentium, standard servers, they don't scale very well, when we're talking about the low load and high load. So if you running some, very computationally intensive task on your server, and it's getting pretty hot, so you have to use the coolers and the fans. But when it's idle, when it's not processing anything, it's still getting hot. It's not. It doesn't go to sleep, and this kind of scalability is the problem. And this chip does exactly what's required. When it's calculating something, it consumes. Well, actually, it consumes pretty efficiently. But when it does not calculate nothing, it just instantly goes to sleep. So it doesn't consume anything. And this is a very important feature of this design. And that's why we call it greenest chip in the world. And this is nice looking color slide. Oh well, you know what? I think I should tell you about how the functionality was mapped to this chip. Okay, so first we've got these two cores which talk to the external codec, and we're using external codec as the to convert digital to analog and to analog to digital. And initially, I wanted to use the internal digital analog and analog digital converters chips, but then I figured out that the price for the amplifier you still have to use to connect to your microphones, and it can't be just simple amplifier, because you have to provide it have to provide me with 24 bits of the dynamic range. So you have to use some complicated preamps, with the controllable gain or logarithmic preamps, something like this. So the cost of this device would be higher than the cost of the standard codec, which has the amplifiers and decks and ADCs inside. So, and it's the one we're using, it costs about $5. And the price is low because a lot of MP3 players using this codec. So it's very mass production. So we decided to go with this codec, and it made our life much easier. Anyway, so these two cores, they talk into the codec. This is getting the input signal, and this is to the speaker and sending the digital audio to the codec to it convert to the is sent to the speaker. So this part is the directional microphone. And after the directional microphone, we've got a chain of the filters. So like I told you, every band is implemented on 2 cores, because it was enough to have 5 second order section to implement each band. So we basically have all 8 of them connected into the chain. So signal basically goes this way. And after the filters, we've got this 4 cores running the all-pass filters. In here we have a logarithm, and although we're running the chordic at this core. This is why it's pretty busy, because we calculate the logarithm for every band. So it's kind of doing the multiplexing the calculation. And this is the exponent, and of course exponent is supposed to be fit with the parameters. So, and this is the division, and this is where we put the signal, all 8 channels together. So it's kind of mixer, and this is just pipe, because we couldn't connect it this way. And then we kick it out. So we're running the driver of the codec in here. And what?
Why is the input block so much more busy than the output?
Well, because this is a simulation, and during the simulation we were reading the from file, and the test bed was done just this way. So we just do the constant pulling. When it's ready, we kick it out. So in a real life, what? Even in the real life, it will be this way, because we're using the clocks generated by the codec, and to generate the proper bits, you're supposed to detect the both front and rear edges of the pulse, and there is no way you can detect the rear edge of the pulse using this core. So you have to pull constantly to detect the end of the signal. So even not in the simulation, even in the real life, this core is supposed to be busy. So if I believe in the next generation of the chip, this issue, it's not a big issue, but it's still a small issue, is going to be solved. So it will save for me a couple of milliwatts. But yeah. Okay, and these cores, they were not involved in the simulation because, but it doesn't mean that we don't use them, because this core is connected to the flash memory, so it's booting the application from the flash, and this core is connected to the RS-232 interface, and basically we can boot from the flash and from RS-232, and we use both of these methods of the booting in our application. For example, the device can work in 3 different modes. Standalone mode, when it's not connected to the PC, and when it just boot from the flash and running the algorithm, and 2 testing mode. And according to 1 testing mode, it will boot from the RS-232 with the payload sending to the device from the PC, and then it will play the streaming audio, the audio which streams from PC. And all the compression and amplification parameters are interleaved into this audio. So basically you are streaming different kind of audio tests from PC, and you change smoothly the hearing aid parameters, and you figure out with which combination of parameters you hear this test audio better. And the third mode it's also the testing mode. It's very close to the standalone mode. The only difference is you are listening to the real environment, so you are connected to the microphone, but you still are receiving the hearing aid parameters through the RS-232 connection from the Note 33. And Note 34, 35, and 36 is basically some kind of elbow room for us. So if, okay, let me just.
You can take a couple of quick questions or wrap up.
Okay, so this is the code gems. I believe I just will. And this is how we do the 53 bits multiplication. And this is the layout of the whole system. And this is how the device looks like. And I've got it in here. And this is how it compares to Texas System and DSP. In 2 words, it's 20 times more power efficient. And we're talking about the best embedded TI DSPs. And this is very fair comparison, because this DSP is designed to do the audio processing. So it's not something it's not comfortable with. And even comparing to this specialized device, we are 20 times more power efficient. We consume 1 watt, we consume 55 milliwatts. And this is how it compares. So this is the board, TI boards used for the initial prototyping, and this is my device. And this is myths and legends. So we were told that RAM, 64 words of RAM is not enough for serious application. Hearing aid is serious application. And yeah, of course, sometimes we were not that comfortable with this amount. We wanted it to be more. But finally, it's working with the 64 words of memory. So 64 words per core is enough. The other legend was amount of I/O pins is not enough. For this particular application, we've got extra 46 pins we don't use. So we could survive even with 64 pins less. So it's not an issue again. And the existing tutorial is to basic no GUI, no C compiler adds. We're really comfortable with what we've got. And when we needed to build something special, like Heatmap builder, we just did it on top of existing toolchain. That's it. Thank you. I'm sorry. I was.
You can take a couple of questions.
Okay, I can pick a couple of questions. Yes.
When you did the comparison of the external versus an on-chip codec, how many quarters did it take to do the on-chip codec? I know you didn't have too many to spare.
The thing is one core. It could be one core, but the thing is, I could figure out how to build a very high quality DA converter, digital analog converter, but I doubt that I could build 24-bit A to D converter. So it wasn't about how many cores. It was about, is it possible?
The processing issue was resolute.
Yes.